So hi everyone. Do you see my screen? And
Yeah.
yeah, I think the slide control. Yeah, it works. It works just fine. All right, thank you. So hi everyone. My name is Zhenrui, and I'm glad to be here at RecSys 21. I'm introducing our work, black box attacks on sequential recommenders via data-free model extraction. So this is a work by me, Zhankui, Huimin, and Professor McAuley at UC San Diego. So let's get started. So first of all, I'll shortly talk about sequential recommenders before we proceed. So sequential recommenders are specific recommender systems that take sequential input at a time, which would normally be user history of clicks or buys. And in our setting, it returns a list of recommended items. And state-of-the-art examples of such recommender systems include SASRec, BERT4rec, NARM, and GRU4rec. So there are a few previous works in model extraction and adversarial attacks. We consider both aspects in recommender systems and specifically in RecSys model extraction. We are the first to have a data-free setting, and the black box model only returns a truncated ranked list rather than a full distribution of recommended items. And we also propose AutoRegressive data generation, which significantly improves extraction performance. And as for adversarial attacks, we designed approximated algorithm based on the extracted white box model to quickly generate adversarial examples, which proved to be very effective in both attack scenarios. So the objective of this paper is to perform targeted attacks on sequential recommenders, which means to bias recommenders towards recommending certain target items. So this is possible in two kinds of attacks: profile pollution and data poisoning. And however, adversarial attacks heavily rely on the model weights, and it's extremely difficult to attack without prior knowledge of the black box recommender systems. So this naturally leads us to the idea of model extraction. With model extraction, we want to make a local copy of the black box recommender, and the copy should be as close to the black box model as possible, so it could provide accurate prior knowledge. In our paper, we assume the recommender API is available to attackers, and the API will return a ranked list of K items, which is in our case 100 items, according to the output scores in the descending order. And naturally, attackers will have no access to the training data and will be blocked if API calls would exceed certain number. So to provide information for extraction, we need to generate informative data and corresponding labels, which give us the first step, synthetic data generation. So for synthetic data, we propose autoregressive data generation. This is inspired by the autoregressive property of sequential recommendation. So similar to language generation, the current decoded output can be appended to the input and form a longer sequence step by step. So we start from some items and we input these items into the black box model, and we sample from the output ranked list. And then we append these sampled items to the input sequences. This process can be repeated until the sequences are long enough. So the returned items can be recorded as labels for model extraction step by step. So in this way, we can sample synthetic data autoregressively and use them to train a white box model. Now, let's go back to model extraction. We mentioned before that in our setting, black box models return ranked list. So in the white box model can be initiated and accessed, so which means we actually have the probability distribution of the next item recommendation in the white box model. So that being said, we now need an objective function that measures the distance between the probability distribution and the ranked list, which is from the black box recommender, such that the differences between the white box model and the black box recommender can be minimized. So to compute the loss, the loss, we designed an objective function which measures both the recall and the ranking performance of the white box model. In this formula, SW represents the scores of the white box output, but only the same items in the black box ranked list and in the same ordering. And S negative refers to the negative items, which are simply items that are not in the recommended ranked list. And both terms are margin ranking losses with different margins. On the left side, we emphasize the ordering of the white box scores, namely the ranking part, and by putting the penalty to the neighboring items if the latter items have higher scores than the previous items, which indicates wrong ordering. And similarly, on the right side, we sample k negative items and applied penalty when negative items have higher scores than the output items in the ranked list. So this term corresponding to the recall. And as for the two margins, lambda 1 and lambda 2, this can be determined empirically, and lambda 2 is usually much higher than lambda 1. So let's take a look at our overall framework. The left part of the figure represents the black box model not under any attack, and we can generate autoregressive data to extract the white box model. And it can be used to generate fake profiles and data poisoning. And in the former case, we pollute the test time data to attack, and in the latter case, the retrained recommender would ideally carry the bias of the poisoning data and recommend our targets. So first, we'll talk about profile pollution attacks. Here, we simply append a few adversarial items at the end of the user log or of the user history and evaluate the exposure of target items. So the embeddings of adversarial items can be first computed with TFGSM, which is a common method for generating adversarial perturbations. Then we compute the cosine similarity between possible items and the adversarial embeddings we just computed. We choose among the items with the highest similarity scores. Note that in this type of attacks, black box recommenders are not retrained. We simply want to achieve the target promotion attack by changing the test time data. And now let's go to the second setting, which is the data poisoning setting. Here we follow the co-visitation approach, namely with the item pairs, one of the common ways for data poisoning. So the item pairs are created in target and irrelevant item pairs. And by repeating such patterns, the recommenders can be biased and connect irrelevant items with the target. And in our case, idea is a little bit different. We want the next item to be the target, even if input sequences are most unlikely items. So we start from some sequences and we compute adversarial embeddings with TFGSM, which is the same as profile pollution. But when we choose items, we tend to choose the ones with the lowest cosine similarity instead of the highest, so that our co-visitation consists of some very irrelevant or very unlikely items and followed by the target. We want the retrained recommender to carry such bias so that even in very unlikely situations that the black box recommenders would still be recommended targets after retraining. So let's go to our results. So we use NDCG and recall to evaluate our models, and we use agreement to measure the distance between the two model outputs. So agreement is similar to IOU, but with K in the denominator. And from the results, we see that the autoregressive data clearly wins a random data approach, and the average agreement is way higher than the models trained with randomly generated data. You can see the numbers on the right columns. And NDCG and recall matrix revealed that the overall recommendation quality of the white box model is also very close to the black box model. And note that the randomly generated data also have labels that are from the black box recommenders. So you actually have the same API budget because it needs the labels, and only the sequence itself are random. And additionally, we consider cross-model extraction. Here, the horizontal axis is the white box model and the vertical axis is the black box model. The metric here is agreement at 10, and darker colors stand for higher agreement. We see that NARM performs generally very well and the best in almost all cases. And the same model distillation would usually yield better performance than cross-model distillation. Now let's go to the profile pollution part. The data poisoning part. Here we set the label to be one of the target items, and we just a second, I'm sorry. The data poisoning, we follow exactly. So we inject only 1% of the user profile here, and the target is one of the 25 items in the target group. And we see similar trends in the previous results. So this time, our extracted model can sometimes outperform the black box model, which suggests that the bottleneck here is not the similarity between the white box model and the black box model, but the algorithm. And the relatively minor improvements is mostly due to the target group and the limited injection profiles. So in this work, we investigated the black box attacks on recommenders and proposed to use distillation to create a local copy of the recommender. And results suggest that the attacks can be achieved by this local copy and can be transferred to the black box model. And here are a few takeaways. And first, the autoregressive data helps narrowing the distance between the black box model and the white box model. And NARM has the overall best capability in simulating the black box recommenders. And also denser data sets and more API budget will lead to a strong extracted model. Another thing is that we noticed popular items are usually more vulnerable on the profile pollution attacks, while in the other setting, data poisoning is usually much more helpful to perform data poisoning if you are targeting on less popular items. So that's our work. That's my presentation. Thank you. And I'm ready to take questions.
Thank you, Zhenrui. Any questions on site? So I have a question myself. From your work, would you conclude that some models are easier to attack than others? And you also mentioned as future work to extend or your work to other types. So first, how general is your approach for different models? And do you think that some can be more difficult than others to attack?
Okay. First of all, it's true that some recommenders are more vulnerable in model extraction and adversarial attacks. And for example, NARM in our experiments and RNN-based models are generally more vulnerable than transform-based sequential recommenders. And for model extraction, that's the case. And for adversarial attacks, I think most models are very vulnerable in the case of profile pollution. And for data poisoning, these models are actually less vulnerable in considering the 1% data poisoning profile setting. So that's what we have from our experiments. Does that solve your question?
Yeah, thank you.
Sure.
Another question from Kjeld Lundgaard is, do you have measures for how many interactions you need for creating adversarial results?
I can't follow. Can you repeat the question?
Sure. Do you have measures for how many interactions you needed for creating adversarial results?
Okay. So in adversarial results, for example, in the profile pollution settings, we have appended 2 items or 10 items in the user log, appending to the original user length. And in the data poisoning settings, we only use 1% of the adversarial profiles based on the original data size.
Okay, thank you very much. In the interest of time, we need to move on. So thanks again to our speakers.
Thank you.
Thank you.